Let's take a minute and discuss that inferential statistic, the correlation coefficient. It's abbreviated with the lowercase r. I know, see, it uses an uppercase r. We should probably write and tell them that it should be a lowercase r. This is a number, so r is a number that's between -1 and +1. And that single number tells us both the nature and the strength of the relationship between two variables that were measured continuously. It tells us the nature of the relationship because it's either a positive number, r is greater than 0, and that is described as a positive relationship where there's a positive slope to the line and increases in the x-axis are associated with increases in the y-axis, decreases in the x-axis, decreases in the y-axis. The other nature could be that it's a negative relationship, that r is less than 0, that r is a negative number, and that the slope of the line is negative, that it goes down as we go from left to right. And so as the y-axis increases, the x-axis is decreasing. So a small x-axis value is associated with a large y-axis value, and a large x-axis value is associated with a small y-axis value. As x goes up, y goes down. As x goes down, y goes up. That's a negative relationship. They go up and down opposite of each other. So they go up and down together, or they go up and down opposite of each other. The other possible outcome is that r basically equals 0. R is really close to 0. And that would be no relationship at all. That knowing something about x doesn't really tell you anything about y at all. And this is where we'd see that circle being really quite round in order to contain 95% of those data points. The other piece of information that r gives us is the strength of the relationship. And we evaluate the strength of the relationship based on the absolute value of r. So if r is less than 0.1, if the absolute value of r is less than 0.1, there's no relationship. That's 0. If it's between about 0.1 and 0.3, we would call that a weak relationship. If it's between about 0.3 and about 0.5, we would call that a moderate relationship, and more than 0.5 is a very strong relationship. We get pretty excited in the social sciences about even quite weak relationships. Here are some examples. So this is a positive relationship and it's very strong. The dots are very tightly clustered. Here is that negative relationship and it is also very strong. The dots are incredibly tightly clustered. It would be so easy to draw that line of best fit, wouldn't it? This is a positive relationship, but the cloud of dots is far more spread out. And so this would be a weak positive relationship. This one is certainly a negative relationship. There's a little more variation there. It would count as a moderate negative relationship. And then here's a weak negative relationship. You can still see where the line of best fit would go. And then there's that example of none. There's no way to draw a line there. Or the line of best fit would just be right at the average. We would just calculate the average of the y value and put the line just right there. The r value that we've calculated, 0.16, and so that's a positive number. As one increases, the other increases. As the years have gone on, the age of the actors has increased. 0.16 is in the weak range. It's a weak relationship. If there was actually no relationship between the variables, if we had this situation, it's very likely to calculate an r close to 0, up to about that 0.1 place. And it's very unlikely to calculate an r larger than 0.1. We need to take a little bit of a risk when we're making a decision. We're willing to decide that the relationship is real if the probability of calculating that r, if by chance, was just less than 5%. You're going to see this written as p is less than 0.05. For this class, we're just going to use this table of weak, moderate, and strong. But be aware that you will also see the associated p-values. Also, this table is not taking into account sample size. The larger the sample, the smaller the relationship that you can detect. So even a very weak relationship of 0.11 or 0.16 can be detected if you have a large sample size. One of the reasons that we calculate a correlation like this is so that we can make predictions. I mean, in this case, we've got the entire population, so we're not really interested in making predictions to other people. But imagine we were. Imagine, let's say we discovered that there was a data point from 1945 that we had missed. What would be our best prediction about the age of the winner in 1945 if we knew all of these other ages, but we didn't know that one particular data point? In order to use this to assess that, we would find 1945 on our x-axis, and we would follow that up to the line of best fit, and then we would follow that across to the y-axis and see what value of y is associated with 1945 for the value of x. And so we'd maybe predict that the winner would have been about 39, just under 40. But how confident would you feel in that prediction? When we look at, the range of values from 1945, well, we would have to give a pretty wide range, wouldn't we? We'd have to say somewhere between 30 and 50. We wouldn't feel hugely confident in saying 39 or 40. Let's explore a little bit more with correlation coefficients. There is an interactive website that's called Interpreting Correlations. Just as an aside here, he's just using the word correlations. He's using that as an abbreviation for correlation coefficients. We tend to use that word just to mean a correlation coefficient. And so you can see that he's using that as an abbreviation because he's got here the correlation coefficient. Let's see if we agree with what he says. Summarizes the association between two variables. Okay? So we've got variable A and variable B, and at the moment they're not overlapping at all. And so if variable A was plotted along the x-axis and variable B was plotted along the y-axis, we'd get this pretty random cloud of spots here. We can click and drag that slider down, and this is what a correlation of negative 0.4 would look like. So it's got a negative slope, and it's a pretty wide cluster of spots, of data points. If we take it down to, let's say, negative 0.7, again, we've still got that negative line, but the data points are far more tightly clustered. And if we go down to a perfect negative correlation, oh my goodness, look how tightly clustered those data points are. They're all right along that line. And you can see the shared variance, the amount of overlap between the two variables. That's the other part that he's talking about here, that with that perfect negative correlation, they share all of their variance. They are totally overlapping. And as we go back towards 0, we see that line just becoming flat and the data points just being spread out. And as we go the other direction and we get to a weak positive correlation and a moderate positive correlation, and then these extremely strong positive correlations, we can see the slope is now positive. Increases in one variable are associated with increases in the other variable. And as we get further and further out towards positive 1, those data points are clustering tighter and tighter and tighter onto that line of best fit. And you can see the shed variance increasing as well.